I'm delighted to be here. Thank you, Thomas, for the great introduction. And again, I'm contrasting the old and young earth paradigms. I think I want to generalize that to maybe young and old universe or creation paradigms. And of course, the old paradigm could include old age creationists of some sort, theistic evolutionists and such. And it also includes people who don't believe in creation of any kind, to be evolutionists. And so some of what I will say perhaps would be more appropriate to them. But you know, there really are just two explanations of how the world came to be, how we and our world around us came to be. One of them will be evolution, which I will try to define very broadly as a purely natural, purely physical process. Now, if they're an evolutionary biologist here, they would be jumping up and down and getting really upset and saying, no, that's not it. It's variation in gene pool frequency, or it's descent with modification or something along those lines. But you see, evolution is not just about biology. It's also in geology. It's also cosmic evolution. It's astronomical evolution. We also have societal evolution, evolution of law, evolution of marriage, all these sorts of things. And if you're going to try to define evolution broadly enough to encompass all those areas of human endeavor, you're going to have to do it very broadly. And the point is, evolution at its heart, if you really understand what it's doing, what you're trying to do with it is you're trying to explain the world totally apart from a creator. That's why I find theistic evolution to be oxymoronic. Because if you really comprehend creation, you don't need evolution. If you truly comprehend evolution, you don't need a creator. You can take and mix them together about as well as you can mix oil and water. They'll mix for a while, but they won't stay mixed. They will separate out very quickly. The contrast to that, of course, is creation, which I'm going to define as a supernatural explanation or process of how the world came to be. And that, too, is awful broad, perhaps too broad, because someone might come away thinking that it's just any god or gods, or even some sort of a non-personal entity that's responsible for creation. But I want to make it very clear I'm talking about the God of the Bible here. I'm not talking about any other form of creation. But I did want to kind of define it broadly in that sense. And is it important what we believe about this? Is it important what we believe about creation? And I think the definite answer is yes, because we're going to have a very different approach to how we interpret the world. As a Bible-believing Christian, someone who believes in creation, believes in a personal creator who is very much involved in the affairs of the world, I'm going to look at the world very differently than would others. I see purpose and I see design. And at this point in a talk like this, I could go off in the design direction and talk about design. Or I could talk about other things that I'm about to do here. You see, one of the important discriminators here is a matter of time. And the reason for that is the fact that evolution requires a very long period of time, millions or even billions of years. You see, we don't see new forms of creatures coming into existence before our eyes. We see pretty much the same creatures we've always had. We see some changes within those groups or kinds, but we don't see one type forming into a totally different new type. Geology, we see all these mountains around us, but we don't see mountains forming before our very eyes. In astronomy, we don't see much going on there either. We see a lot of stasis in all of these things. So if evolution is the true explanation of how the world came to be, then the only resolution to that paradox is that evolution must be very, very slow, so that even over many human lifetimes, no appreciable change is really noticeable in the world. But over eons of time, those small changes will add up and become more obvious. On the other hand, creation was a fast process. A couple of reasons. One is the fact that there's no need for great time. If you really understand the nature of creation, you can just have things come into existence pretty rapidly. No great time required. And someone may protest and say, well, wait a minute, aren't you kind of limiting God? Couldn't God have created over billions of years? And the answer is yes, God could have created over billions of years. But I'm not limiting God in that. I think God is limiting God in that, because you see, He's revealed His timing to us in Scripture. We have 6 normal days, and people much better qualified to address this issue of what those days mean, or could it do better. But I will just cut to the chase here and tell you that there are very good contextual reasons for believing these are normal days. And then you could have to look at the genealogies and other chronological clues you find in the Bible, and we find that the creation was maybe a little more than 6,000 years ago. Now that's quite a contrast to, say, 4.5 billion or 13.8 billion years ago, which is what the age of the Earth and solar system and also the age of the universe is supposed to be. And you might want to try to stretch out the chronologies and genealogies a little bit, but that's not going to get you anywhere close unless you do total damage to those historical clues found in the Old Testament. So it's my opinion that age ought to be a nice discriminator between two types of models here, be it an old age creation or a new recent creation, or be it evolutionary one. Whenever you have this division between billions of years and only thousands of years, then age ought to be a discriminator on these sorts of things. And so it's my job, part of my job as a creation scientist is to attempt to build a creation model. And I've been working away at that for years and making some modest progress, I think, on this project. But another one is to give people some good reasons to believe that the creation is not billions of years old. Is there evidence out there that they suggest that the universe or the world or the Earth, or the solar system, stars in general are much younger than billions of years? And I think we can find that if you're looking in the right places and interpreting the data in the proper way. Now, I've been doing this creation science stuff for 4 decades or more, and I've come to some interesting conclusions about this, thousands or billions of years. I long ago came to the conclusion that the answer to this has very little to do with physical evidence. It has very little to do with physical evidence. When you confront someone with difficulties with indications of billions of years, and you provide them with evidence that suggests the universe is much younger than billions of years, they tend to minimize the evidence you give and minimize the problems with the billions of years, because they have a vested interest. They've got a lot of time and equity built into these things, and it's very difficult to change their minds about it. In fact, it's more of a heart issue, change their hearts to then change the mind. That's the order it ought to be in. And you come into it with a ton of assumptions. Any scientist who says that they're just objectively looking at the world and just looking at the answers, and the answers just plop out, they don't really understand the nature of the whole enterprise here. I think many people erroneously get the idea that scientists just were minding their own business. They went out into the world, they just started looking around, how old is the world, with no preconception at all, and the evidence just simply led them to the conclusion it must be billions of years old. Is that pretty much the impression you get from a lot of science programs you watch and a lot of things you read out there? That's certainly the impression I would get. But that doesn't work because I've known too many scientists. Okay, we have a ton of assumptions. I have a ton of assumptions that come into this. The only difference is I don't try to pretend that I'm totally objective. I will tell you what my biases are. But many people are not even aware that they have biases. If you're aware of your biases, at least you can attempt to compensate for those biases. But if you pretend you don't have any, then there's no way in the world you can properly compensate for that. Let me give you an example of what I'm talking about, though, how that evidence has very little to do with it. I'm a student of history. If you've heard me speak much, you'll hear me talk about the historical context for things. It's interesting. At the end of the 19th century, toward the end of the 19th century, biologists and geologists were convinced, I should say, that the world was at least 100 million years old. Now, what had led them to this conclusion? Well, it had nothing to do with going out and just making measurements and finding out, well, what do you know? The age of the Earth really is 100 million years. That had nothing to do with it. This conclusion was based entirely upon the assumption of evolution as the explanation of how things came to be. Biologists looked at the diversity of plant and animal life, and they estimated at the time that it would have taken at least 100 million years to account for the diversity that we see. Now, in order to get that, you had to assume some rate of evolution, apparently, to reach that conclusion. It wasn't very quantitative. It was a very qualitative assessment at best. And again, I think this is a minimum figure. Most of them would have wanted more than that, quite a bit more. Geologists similarly had made the same conclusion. They had looked at river valleys and say, well, how long did it take this river here to erode away this valley? How long did it take this mountain to be pushed up? And it's being pushed up now, and we don't see it, but it must be a very slow rate, and we can multiply that, and we get at least 100 million years. Again, no quantitative analysis going on, just simply an estimate based upon the rate at which evolution would have to occur in order to account for these effects. Well, at the same time, Lord Kelvin, he was one of the most eminent physicists of the 19th century. He looked at the situation, and he looked at the Earth and the age of the Earth, and he looked at the sun and got the age of the sun. He assumed that the Earth started off with a molten mass, and it cooled over time, and as it cooled, the surface solidified, and they still had some heat inside, and heat was going away from the inside to the outside. And if you tunnel in deeply into the Earth, we find a temperature increase. We call that a temperature gradient with depth. And from that temperature gradient that was then measured and the rate at which heat was leaving the Earth, he was then able to calculate using some pretty well-understood physics and some well-understood properties of matter and mathematics that the maximum age of the Earth was maybe 20 or 30 million years old at that point. That's a maximum age because, you see, he assumed that the Earth started in a molten state. If it didn't start in a molten state, then the age would be far less than that, wouldn't it? So it's a maximum age, 20, 30 million years. Now, he did a similar thing for the sun. At that point, people thought that the sun was deriving its energy from contraction of the sun. That's called the Kelvin-Helmholtz mechanism. By the way, astronomers today still think that mechanism works. It would work in the early stages of star formation and life cycles of stars and at other stages at various points, but for the most part it wouldn't. I'll say a little bit about that in just a minute here. But the point is, he then did this calculation for the rate at which assuming the sun started off as a very large distant mass and contracted down, converting gravitational potential energy, and he found out the maximum age of the sun would be 20 to 30 million years, no more than that. Again, a maximum age, it could be shorter than that. So here he did two relatively independent methods, one on the Earth, one on the sun, and they converged on the same value to within about a factor of 2, less than a factor of 2. And again, a maximum age indicating something less than that. Yet many scientists at the time were persisting in believing that the world was much older than that, at least 3 times older, if not much longer. So a couple of observations I can make here was that the belief in the old Earth at the end of the 19th century was based not because of the best evidence, but in spite of the best evidence. All numerical measures of the age of the Earth and Sun at that time screamed that the age was far less than most scientists wanted. But they ignored that, thinking that there must be some other source for the Sun's energy, some other source for the Earth's internal heat. As it turns out, we later on did find sources for those: nuclear fusion for the Sun and its core, and radioactive decay for the interior of the Earth. That's not my point. Some people at this point say, well, they were wrong. Well, fine, they were wrong, but you're missing my point. My point is, at the time, based upon the data they had, the quantitative measurements flatly contradicted the majority opinion concerning the age of the Earth. Ergo, evidence had nothing to do with it. That's my point. The great age at that point was based entirely upon the assumption of evolution. Again, I want to be very clear. I know that we have a different theory and understanding of the source of the sun's heat and the source of the Earth's internal heat today. But that's not the point. The point is people persisted in an incorrect belief beyond the age the limits could be given at that time, merely because their presuppositions were wrong, I am convinced. Now, has the situation changed much today? People believe the Earth is 4.5 billion years old. They believe the universe is 13.8 billion years old. They claim this based upon some measurements of data, but a lot of that belief already preceded that data. The belief in great age did. And so again, I don't think the situation's changed. They trumpet and they marshal up these different quantitative measurements, but I don't think that that's really getting to the point of the question. And again, I want to reiterate that creation account in Genesis 1, it's very clear it's talking about the miraculous. And again, God, I'm not limiting God by saying it had to be 6 days, not too long ago, because God has limited himself. He has told us, revealed to us in the Bible that how long this took. Now, you could argue, some people argue, well, the Bible, we take two approaches to this question, two ways. One, we could start with the Bible And the other one, we can start with what people think science is. Now, already there's a little bit of a shifting argument going on here. It's almost as if the Bible and the science are similar things in some way. Well, they're not. Science is a human-inspired way of how we go about trying to study the natural world around us. And we don't argue with most of science. If you sit down and start thinking about the discipline of science, there's very little we would quibble with. I taught physics for many years, and there really wasn't much of anything there I could argue with in physics. Whether you're an evolutionist, an atheist, a Christian, a theist, a Bible-believing Christian, a creationist, doesn't matter. Physics is physics. When you get into astronomy, my primary discipline, much of that doesn't depend either. There's a lot of descriptive astronomy, a lot of operational astronomy, if you will, based on what we see around the world right now. And then there's this historical aspect, and I had very little to quibble with there. In the years I taught astronomy at the university, there was relatively little that I taught that I disagreed with. When I did get to evolutionary ideas, and yes, I did teach them in my classrooms, I also felt free to critique those ideas. I often said anybody that came out of my second semester of my astronomy class believing the Big Bang must have not been paying attention in my class. All right, again, we sometimes talk about the fact that there are two types of science, and a lot of the critics, a lot of the evolutionists don't like this, but I think it's very appropriate. We have what some of us call operational science. That's a science of the here and now. It's based upon what we see around the world. And then there's historical science, or if you will, origin science, people talk here. It's talking about past processes. It's like forensic science. You know, you can put together this theory about what have happened in the past, but how can you, short of a time machine, how can you actually go back into the past and test to see if that's exactly what happened? The rules of the understanding and testing these two approaches are very different from one another. I won't say that historical science is illegitimate. I'll simply say that it's very different. Sometimes people will say disbelieving evolution is like disbelieving gravity. And that's nonsense. We can make up different theories of gravity. In fact, people do that. And you can go into the lab and test those different theories. In fact, there are experiments going on right now that do that. And you can then figure out which theory is supported by the evidence and which ones are eliminated by the evidence. But you can't really do that with origin science. You can take the evidence as it exists, say fossils existing in the present, and try to deduce what might have happened in the past to explain those. That's the way historical science works, but it doesn't tell you exactly what happened. You can't test the same way. So we'll say that the Bible is not a science book, and I happen to agree. But you know what, folks? We're not necessarily talking so much science here, we're talking about history, and the Bible is a history book. The first 5 books are clearly historical books. The Pentateuch, plus you've got 12 more, giving you a total of 17, but hold on a minute. You've got the prophetic books, and they contain a tremendous amount of history in each of those. And then you go to the poetic books. One of them, Job, is a historical book as well, told in a poetic form. So already, but 4 of the Old Testament books are history. And then you have the Gospels and the book of Acts and the New Testament. They take a bulk of that. Those are history books. Many of the epistles contain historical clues as well. Book of Revelation, well, I'll leave it up to you to decide how much of that is history. Okay, that's a big debate I don't want to go to there. My point is this: the Bible is a book of history. If we're going to talk about the history of the world, then as a Christian, it behooves us to start with the Word of God. So the length and age of creation, again, I keep repeating myself, but it's very important. I do believe the creation week was 6 normal days. The genealogies and chronologies suggest a little over 6,000 years. And again, the question leading up to the conclusion of my introduction is, can we find evidence of this? And the answer, I think, is yes. Okay, we have here an image of the moon, and some of the stuff people earlier in the week have mentioned, so I'm going to go quickly through some of this. And one of the things we find here is that we have a magnetic field on the Earth, and the man named Thomas Barnes back in the 60s and 70s was talking about this, and he was arguing then, based upon what he knew about physics and what generates magnetic fields, that these fields must decay, and indeed measurements going back now 180 years of the measurement of the Earth's magnetic field shows that it is indeed decaying. And from that, he argued that the magnetic field of the Earth must be very young. And Russ Humphrey's name has been mentioned here. He took up the mantle from Thomas Barnes, and he's actually improved upon it tremendously, and to help us understand the Earth's magnetic field better. But he's also used his theory to to correctly predict the magnetic fields of Uranus and Neptune. They were measured in 86 and 89 respectively, and he published his predictions in 1985, 1 year before the measurements of one and 4 years before the measurement of the others. And it turns out he got the measurements pretty good. His predictions matched the measurements pretty well. Not nearly the evolutionist predictions didn't match nearly as good. They always say that you creationists don't make any testable predictions. Well, I beg to differ. 30 years ago, Russ Humphreys made some testable predictions. Stay tuned. He continues to refine this, and other creationists do as well. Here we have an image of the Earth-Moon system. We like to call it the Earth-Moon system sometimes because the moon is rather large compared to the Earth, both in diameter. It's only 1/4 the size of the Earth. The Earth has 81 times more mass than the moon has. But when you compare it to other satellites of the solar system, the ratios of sizes and masses are pretty close here. In the case of all the others, the masses are generally thousands or even tens of thousands or millions to one rather than 81 to 1. And the sizes, they're little dinky things. We looked at Jupiter the other night through the telescope, and you could see the disk of Jupiter, couldn't you? Could you see any disk on the satellites, though? No, they're very tiny. They are much smaller. If you were looking at from another planet looking at the Earth, you would see the Earth and you'd see the moon. The moon would be about 1/4 the size of the Earth. One big difference, though, is the albedo or reflectivity of the Earth is much greater. It's got a lot of water and clouds, and they reflect much better, and the atmosphere does too, than the moon does. In this particular image made by one of the Voyager spacecraft on the way out on its mission, they had to increase the contrast for the moon. If they left it uncontrasted, it would barely show up. The moon's pretty dim compared to the Earth. The full Earth on the moon, I understand, is quite a sight to see. It's 16 times bigger and a lot brighter. It really floods the landscape with light. Well, I think all of you, most of you have been near the ocean. You're familiar with the tides. Each day the water rises and falls twice, high and low tide. What you may not know is that there's a complex interaction that's going on between those. We call it the tidal evolution. It's okay to use that term, evolution, the other word there, of the Earth-Moon system. And what happens is a very complex interaction. I don't have time to talk about the physics too much, but the tidal bulge of the Earth is raised here. Here's the moon. You got the tidal bulge of the moon's over here, and the tidal bulge of the Earth is like this. The Earth's rapid rotation takes that bulge forward like this. So you got a bulge here and the moon right there. Well, the moon pulls on that bulge. It takes this near side of the bulge close to it and kind of pulls it backwards like this. And it takes the other one and kind of pulls it forward. And since this backward one is stronger than the forward one, it acts as a brake and trying to slow the Earth's rotation. The Earth is rotating this way, and the moon's trying to grab that bulge and pull it back that direction. It's very feeble. The day is actually getting longer. We've measured it from historical eclipse record. The day is getting longer by about 16/10,000ths of a second per century. Yeah, you might have missed that, okay? It's really easy to miss 16/10,000ths of a second per century, but it's measurable over many centuries. All right, so that happens, but there's also an action-reaction principle, Newton's third law of motion. So as the moon pulls on the Earth pulls back on the moon. So this bulge pulls on the moon, and the front side, close to the moon, pulls the moon more than the other side does, and it tends to accelerate the moon forward in its orbit. Now, the funny thing about orbital motion is when you accelerate an orbiting body forward, making it go faster, it actually climbs to a higher orbit and goes a little slower then, which means the moon is slowly spiraling away from the Earth. So as the Earth slows down its rotation, the moon spirals out. So each year, the moon's getting a little farther out. How far out is it moving each year? About 4 centimeters per year. So if you want to get a good look at the moon, you better do it soon, all right? Because it's getting farther away all the time. Okay, in my lifetime, it's only gone through my height a couple of times. It doesn't really matter that much, but it does add up. By the way, how do we measure that? Well, when we landed on the moon back 45 years in the late 60s, early 70s. Oh, and by the way, we did land on the moon, despite what some things on YouTube try to tell us. And pretty certain of that. And when they went on the moon, they put these reflectors on the moon, special mirrors, and they use these telescopes, particularly one at McDonald Observatory in West Texas. They take this powerful laser and they hook it to the telescope, and they fire this laser beam through the telescope to the moon. It hits those reflectors and comes back, about 2 2/3 seconds later, and they time the difference, how long it took the thing to come back, and from that they can figure out how far away the moon is to like a fraction of an inch. Do you find that amazing? I can't believe the technology we have. You can measure the distance of the moon to a fraction of an inch. That's incredible. Well, it gets a little more complicated beyond that. You see, the moon's orbit isn't really constant. To a good approximation it is, but it's being tweaked all the time. Other things out there are yanking on it, pulling it around. Other things in the solar system, things going on with the Earth. It's got an elliptical orbit. It's just horrendous, like 20 terms yanking around on it. But we understand those other terms pretty well, and so they make corrections for all those terms. When they get done, they get about 4 centimeters per year. Again, amazing they can do that. So we can take that rate that's measured, and we can then solve an equation. It's a differential equation because we know the rate of lunar recession goes as the inverse 6th power of the distance. Now, if you know, it's 1 over r to the 6th. Now, if you know mathematics at all, you know that's a very steep function of the distance. That means that when the moon was closer to the Earth in the past, the rate of lunar acceleration was greater in the past, much, much greater. So if you take this 4 centimeters per year and extrapolate back for a few billion years, it's not really a problem. But the problem is when you go into the past, you have to account for the fact that the acceleration was more than 4 centimeters. Sometime in the past it was 5, then it was 6, then it was 10, then it was 100, then it was 50, then it was 150, then it was 3,000, and it just takes off as you go into the past. And I've run the numbers on it, and when you do that, you find out that, I say here, less than the Earth-Moon system is less than 1.5 billion years. Actually, it's more like 1.3 billion. I've kind of sugar-coated it here. And actually, before you get back to 1 billion years ago, tides were about 1 mile high. That means here in this part of Tennessee, you would have had beachfront property twice a day. Well, obviously, nobody believes that. So in reality, you run into trouble long before you get back to 1 billion years. I think something like a few 100 million years is probably more like it. Now, this doesn't mean that the Earth is automatically 6,000, 7,000 years old, does it? But it would seem to eliminate anything that's more than about 1 billion years, wouldn't it? Pretty clearly it would, I would think. And so if you're confronted with two possibilities, 4.5 billion years and 6,000 years, or anything else for that matter, once you eliminate the 4.5 billion years, then what do you got left? And we're talking here between those two choices. That's not a false dichotomy here, a false dilemma, because there are really only two on the table we're talking about. If somebody wants to argue that the Earth is 900 million years old, let them go at it, but I don't think anybody is making that claim. Now, there is a response to this. There is a response. The evolutionists are well aware, at least some of them are well aware of this problem, and they have a very good answer for what's going wrong on here. They argue that we live at a time of unusually high tidal interaction. That back after the moon and the Earth formed, there was this tidal locking that went on for about 3.5, 4 billion years, where the moon's orbit didn't change at all. You see, the rate at which the moon's spiraling away, we can't really model that. We can take the measured rate and solve a differential equation to find out the length of time involved, but you can't really model how it's done because it depends very complexly upon the way that the continents are arranged on the Earth. It depends upon the way the upper mantle is arranged on the Earth. All sorts of complex things which are beyond really ability to measure and then model appropriately. But they argue that's exactly what happened, that you had this thing happening so that there was kind of a resonance that occurred for 3.5, almost 4 billion years. And then maybe in the last 3.8 billion years or so, about 3.8 billion years ago, that interaction broke, that locking, and the moon just sort of took off and spiraled ever since then. And when I've been confronted by this, and I have been confronted by some Christian astronomers who do not agree that the world is very young, they think it's 4.5 billion years old, I ask the question, well, that's fine, but where is the evidence for this? Can you give me any evidence? After all, science is supposed to be based upon evidence. And they said, yeah, we got evidence. I said, well, what is it? And what did they tell me? They mentioned simulations people had done. That is, they wrote a computer program to show how this might have happened. And I said, I'm sorry, but that's a simulation. You know, it's make-believe, it's pretend. It shows how well the simulator wrote his code. And I'm convinced you can take a code and write anything you want to prove your point. If you don't, then either A, you don't understand what your task was, or B, you're a pretty bad coder. I don't know. But you can always prove anything by this. But give me some evidence. Give me some predictions you have of this model that you can test. And they don't have any to do that. To me, that comes across as being special pleading or ad hoc. You know, what does ad hoc mean in Latin? Means we're making it up, all right? Oh, it doesn't mean that, but that's what I think it means. Ad hoc means we're making it up. It's special pleading in logic, and I have to ask the question, is this science? I mean, can you do a simulation and claim that this is a science now? This is the evidence. And I'm concerned that in my own field of astronomy, simulations have taken over. Simulations are done all the time now. They just keep doing simulations for this and that and everything else, and that seems to prove that this must have happened. And I suspect it's happening in most other sciences too. They just get carried away in all of this. All right, here we have the planet Jupiter. We looked at it the other night. You could easily see the two dark bands right here on the planet. The red spot's kind of hard for us to see. You need a bigger telescope. And over here you have one of the shadows of one of the satellites moving across. Again, I need a bigger telescope to see that. Back at the observatory at Edges and Genesis, we have a telescope. We could actually, I've seen that little shadow of one moving across. This was taken from a space probe, though. And here we have one of my favorite satellites in the solar system. This is Io. I had a group the other day I was talking to. I always get hungry when I look at this because it looks like a pizza to me. You can see all sorts of nice little spots here and there. And the interesting thing is there aren't any craters on Io. It's the only solid surface body in the solar system that has no impact craters. And that's interesting. How can you have no impact craters? Everything else has impact craters galore in many cases. Even the Earth has impact craters. Well, that coloration on here is due to volcanic eruptions, and the yellows and oranges and reds are due to sulfur compounds. It turns out the volcanic, by the way, here's a nice little image of a volcanic eruption. This is a little movie put together by one of the space probes we've sent to there, and you can see the plume up here on the top. It's going through eruptions right there. The Voyager probe back in 1979, actually, or 77, found, I think, a dozen volcanoes erupting simultaneously on Io. It's the most volcanically active body in the solar system, more active than the Earth is. However, it's not molten rock there. It's molten sulfur, very hot sulfur. That's what that yellow, orange, and red coloration. Sulfur, different compounds can give you different colors. By the way, what is hot burning sulfur, a.k.a.? Brimstone. That's right. Io smells like hell. All right. So you've got this planet, this little satellite Io orbiting around Jupiter. Well, it's the most volcanically active body, as I said. And in order to have volcanically active body, you need a source of heat inside of there. And there are several possibilities. One could be, well, it's primordial heat, but if that is from its creation, but if the world is billions of years old, it should have cooled off billions of years ago. So for the evolutionist or the old ager, that doesn't work. You could argue the radioactive decay of elements, but its density is way too low for that. It's around 3 grams per cubic centimeter, and that would preclude any significant amount of the heavier elements that would fission and produce enough heat to do that. And you could argue, and that's what most evolutionists would argue, that again, they would argue that it's from tidal flexing. The body, as it moves around Jupiter, very strong gravitational field would cause it to flex. If you take a piece of, the moon sort of does this all the time. The Earth does this every day. It heaves up and down twice a day. The rocks beneath you heave up and down by a few feet. You don't notice it, but it does happen. What if you take a piece of metal, like a piece of wire, and you bend it back and forth very rapidly? What happens? It heats up because you're taking mechanical energy and converting it into thermal energy, and they argue the same thing's going on here. And I have a problem with this because I look at it and you have, first of all, the orbit of Io is extremely circular. It's one of the most circular orbits you can imagine, more circular than the Earth's orbit around the sun or the moon's orbit around the Earth. Also, its inclination is virtually zero. It's not bobbing up and down, so that bulge on Jupiter can't really work on it. There's some argument some of the other satellites are tweaking on it and moving around, but there's a problem. The tidal flexing really doesn't work. One of our creation scientists, Dwayne Spencer, a few years ago looked through this, And it turns out when you start analyzing the numbers, it doesn't work either. That's the textbook answer, that tidal flexing will take care of this, but in actuality, when you do the details, the mechanism fails to explain for that. So if you don't have tidal flexing and you don't have radioactive decay, it kind of leaves you back to primordial, which then puts an upper limit to how old this thing is, and it can't be billions, can't be very many millions of years old either, taking us back to, again, creation, I think, recent creation. Tying into that, mentioning craters, we have the planet Pluto. Actually, I'm sorry. It's hard to kill these old habits, but we have the large asteroid, or the dwarf planet Pluto. And here's a close-up image of it, made back 2 years ago with the New Horizons image. I think one of the reasons why so many people like Pluto is because as far along as you had never actually been to it and seen what it looked like, it could be anything you want it to be. Like, for instance, on I-17 north of Phoenix, you go up in this, started going up in this little mountainous area there. Everybody driven I-17 north of Phoenix? There's an exit there for Bumblebee. Anybody ever seen the exit for Bumblebee? And I look at that, and Bumblebee is a wonderful place. You've got peppermint trees, you've got a merry-go-round with a gazebo with a band playing, you got kids playing in the street, you got fruit trees, you got a fountain, you've got springs in there and all sorts of cool things. There's a circus every day and a parade every day. I'm the mayor and they love me there. I told this to somebody once and he said he had been there, and he said, well, don't go there, you'll be disappointed. So I'll never go to Bumblebee because I want Bumblebee to be what it is in my mind. We've been mugged by reality. We've been to Pluto. We know what it looks like now. By the way, do you see Pluto here? There's his neck, there's his nose, and right there, and his mouth, and there's his head. I'm just saying. Okay. Interesting.
Looked at it longer than we have.
How many people see Pluto the dog there? Oh, a few of you do. I see it. It's pretty clear. Of course, I can see constellations and all those stars up there. I got a great imagination. So, anyway, what don't you notice on Pluto? You don't see many craters. In fact, this Pluto head here doesn't seem to have any, and you have a few over there. And there is a very clear shortage of craters. I won't say there aren't any, but there aren't very many on Pluto. Now you see, everybody, I do mean everybody, expected Pluto's surface to be totally covered with craters. Why? Well, because most other objects in the solar system are covered with craters. And where they're not, such as on Io, there's been reworking of some sort to change all of that. And so consequently, if Pluto doesn't have a lot of craters from impacts, then it must have been reworked very recently. But there's no body nearby to tidally flex it, so it can't be that. And there's no, the density is only about 2 grams per cubic centimeter. It's way too low to have radioactive decay to fission to heat the inside. And if it's billions of years old, it can't be primordial heat. So the evolutionist at this point, it's been 2 years, they don't know what to do with it yet. But I look at that and I'm saying, well, wait a minute, if it's only thousands of years old, God could have, made it that way. Could have had volcanic activity on it because it has primordial heat. I don't know, but the thing is, in retrospect, I can account for that. I can explain that. Maybe I didn't predict it, but at least I can, within my worldview, I can actually understand why it's like that. But the evolutionists at this point cannot, because it has to be close to 4.5 billion years old, and it has to have been reworked somehow, but there's no mechanism for doing that. So this too is evidence, I think, of fairly recent creation and ruling out billions of years. Here we have the planet Saturn. This was the, when I was growing up, many of you were growing up, or some of the older people I should say, then this was the only planet that had rings. Now that all changed in the 1970s. First they discovered Uranus had rings, then they discovered Neptune had rings, then they found out Pluto had rings. They have pretty wimpy rings, as it turns out. You can't see them from the Earth. You can photograph them when you send a space probe there, and also you can detect them sometimes from the Earth by occultation measurements, at least Uranus and Neptune you can. Jupiter, that's the wimpiest of them all. And here we have Neptune. It's a it's got the great dark spot sitting on it. That's a very cool planet. Now, rings, I'll talk about the rings in just a minute, but I want to stop here and talk about the Jovian planets for just a minute. There are 4 Jovian planets: Jupiter, Saturn, Uranus, and Neptune. You'll probably recognize those, the four outer planets. The four inner planets we call the terrestrials: Mercury, Venus, Earth, and Mars. Those are Earth-like. Terrestrial means Earth-like, and Jovian means Jupiter-like because they share common characteristics. And what's very interesting is we can measure the heat coming off of these planets. And Jupiter, Saturn, and Neptune give off about twice as much energy as we receive from the sun. Jupiter a little less than twice, but Saturn and Neptune more than twice. That's coming in the infrared. We can calculate how much they absorb from the sun, and we actually can measure directly the energy coming off, and that's very interesting. Because where's that heat coming from? If they are billions of years old, this energy cannot be there anymore because any internal heat would have bled off a long time ago. There's not enough density to account by radioactive cooling, and certainly tidal fluxing won't work on any of these. People have tried to suggest that gravitational settling would happen, but that should have happened a long time ago as well. And so the conclusion most astronomers have reached is that their source of energy is a mystery. Officially, it is a mystery. They have no clue where the heat comes from. Consequently, you don't hear much about that, do you? It's just one of those little oddities. Another oddity is Uranus doesn't do that, but Uranus is a weird planet anyway. Why is it different from the others in so many ways? I'm not sure I know, but the evolutionists certainly don't know. Of course, it's only a mystery if they're very old. If they're very young, it's not a mystery at all, now is it? And again, Saturn and Uranus, it has a ring system. Neptune has a ring system. Jupiter does. Here is a Voyager image of one of the Uranian ring system. It's very different from Saturn's ring system. Saturn's ring system consists of broad rings with a lot of narrow gaps. Okay, the ring system here consists of broad rings and narrow gaps. You're seeing Cassini's division here, but there are many other hundreds or thousands of ring gaps in there. But the other systems, including Uranus, are very different. They consist of very narrow rings with broad gaps in between. That's the reason why they don't show up very easily from the Earth. They've got the Uranus occulted here, blocked out, and still a lot of light is bleeding through. So all four of the Jovian planets have ring systems, but we know the ring systems are falling apart. How do we know that? Well, we can do computations on the orbital motions, and there's a lot of tweaking going on. The other satellites of the system pulling on them and yanking them around. That's why we have gaps. They're pulling material out in those different resonant positions and all of that. And also we have the Cassini and the Galileo probes in the location of Jupiter and Saturn, and they actually can observe, the Cassini could observe and see changes taking place over a matter of a couple of years. Other things going on, you have meteoroids coming through, and when they come at a high angle and hit the ring particles, they blow them out. And so there's several mechanisms well documented that are tearing these things apart. And since they're falling apart so fast, how long can they last? Well, they certainly can't be billions of years. In fact, they may not even be 1 million years old. Saturn's ring system is believed to be far younger than 1 million years. It's a very young thing. And the ring systems of the other three are also relatively young. They think that the other three are a little older because they've dissipated far more. But Saturn, if you hang around long enough, will look like those other ring systems eventually. Now, this is not a real rigorous argument against long age in favor of recent age, because there's a comeback. It could be that there was destruction of a satellite or some other object. You have all this tweaking going on. A satellite could be pulled in close enough to the planet to reach a region called the Roche limit. And the Roche limit is the distance within close enough to a planet where tidal interactions of the planet itself will rip apart a body that's held together by gravity. An object like our own moon and most large satellites in the solar system are held together by gravity, so they are pulled apart at that point. Their gravity is insufficient to overcome or to counterbalance the tidal interaction shredding this thing apart. Now, for smaller things that are held by simply chemical cohesion, some things are held, like small satellites are held together by the chemical bonds between the parts of the rock that they're made out of. They're not subject to this. They're too small for that to happen. Only when they're held together by gravity are they shredded apart. But it's believed that if a particle that's held together by gravity gets close enough to the planet within the Roche limit, it will be shredded and form a ring system. So they could argue that all 4 of the Jovian planets have recently acquired a ring system by some object being shredded apart by its tidal action. But the question I have is, how probable is that? It seems to me to be very improbable, because we just happen to live at a time where all 4 recently shredded up satellites. Just how many satellites did they have to start with, and how many times has this happened in the past 4.5 billion years? Now again, this is a less rigorous argument than the others, but I think it starts to stretch the credulity just a little bit to believe this. Here we have an image of comet Hale-Bopp, and it consists of, like any other comet does, a nucleus down here. The nucleus is a few kilometers across. It goes on a very long elliptical orbit around the sun. Most of the time it's far from the sun, where it's very cold, far from the sunlight, but when it gets in once an orbit to perihelion, the closest approach to the sun's radiation sublimes the ices that make it up, dislodges the dust, forms the coma of the comet, which you see down here, and then the solar wind pushes the gas particles or ion particles away from the sun. That's what this gas or ion tail is. The dust particles are pushed by solar radiation. That's the blue light you're seeing there. So the sun is over to the lower left. Note that the tail always points away from the sun. It doesn't trail behind like a horse's tail would. It's always pushing away from the sun. If it's leaving the sun, its tail precedes it as it moves outward. Now, the comets have very short lifetimes. By the way, the nucleus of Hale-Bopp was the largest nucleus we've ever been able to see in 400 years or so. It's about 40 kilometers across, about 25 miles. Most comet nuclei are just a couple of 3 miles across. It was a monster size. Anyway, short lifetimes of comets. Every time they pass around, they pass very close to the sun. They lose a significant amount of their material through evaporation or sublimation, and knocks off a lot of dust as it does that. Also, occasionally, these things collide with planets. We knew that that was a process that likely happened from time to time. We never actually observed it until 1994, when the comet Shoemaker-Levy 9 hit the planet Jupiter. Actually, 2 years earlier, on its way into the inner solar system, passed close to Jupiter. The tidal effect of Jupiter shredded it into about a dozen different pieces. They rounded the sun. They came back out, and as they did, they smashed into Jupiter, this time one by one over about a week's period of time. And with a small backyard telescope, you could actually see these black spots on Jupiter. They persisted for a few days and then went away as if nothing ever happened to it. In 400 years of telescopic observation, it's the first time we've seen a large impact like that. We knew it was a possibility. Now we've actually witnessed it. And it's undoubtedly happened before. So comets have short lifetimes because of evaporation, because of collisions. By the way, the collision is a catastrophic loss at that point. Also, you can have ejection from the solar system when these comets come close to the planets, particularly Jupiter, because it has so much mass. It doesn't have to be real close, by the way. There can be an energy transfer between Jupiter and the comet, and if Jupiter robs some orbital energy from the planet, it shortens its orbit, which means it comes in more frequently, so it's more subject to the other 2 mechanisms, so it speeds the process up. That happens about half the time, but the other half of the time, it actually boosts the energy, which puts it on a hyperbolic orbit and kicks it out of the solar system, never to return. And this has been observed many times. Many times comets come in, and we know when they leave the inner solar system, they're not coming back because they've gained enough energy to leave. So all 3 of these mechanisms have been observed. And so it's fairly easy to run the calculations, and you'll find that the solar system, the comets we have, must be far less than 4.5 billion years. In fact, they probably can't be any older than about 100 million years, probably less than that, all of them. So this is a pretty low upper limit, I believe, and it would seem to eliminate the solar system being any older than, say, 100 million years, and it could be far, far younger, like, say, 6,000 years, not a problem for us. Now, again, as so many cases we have here, that's not escaped the notice of astronomers, so they have a ready response. Back around 1950, Jan Oort, a Dutch astronomer, suggested that there was a large reservoir of comets called the Oort cloud, very far out from the sun. And these comets are orbiting so far out, we can't see them. They're very dim, and they orbit about. And nothing happens until maybe a star happens to pass nearby, or a large molecular cloud passes close enough, and it jostles the orbits of these things. Some of them gaining energy, lost to the sun, others losing energy, causing them to fall into the inner solar system. So the idea is, as the older comets die out, new comets come in to replace the comets that die off. Now, this explains what we call long period comets, supposedly. Long period comets, roughly 200 years is the breaking point between long and short period comets, but it's not really the time that's involved, it's the type of orbits that they have. Long period comets tend to have orbits that are inclined to any amount to the solar system's plane. There's a plane of the solar system the planets are in, and long period comets can have any inclination from 0 up to 90. About half of them are prograde. They go in the same direction around the sun that the planets do. The other half are retrograde, going the opposite direction. Short period comets have low inclinations within about 20 degrees of the plane of the solar system, and they all go prograde. All right? And we know of probably about 1,000 comets in all of this. So they have the Kuiper belt as this reservoir, kind of a toroidal shape, a donut-shaped distribution beyond the orbit of Neptune that produces the short period comets from gravitational perturbations. Well, the other day Andrew shared this quote, and I'll share it again because he talked about this. This is a great quote. Many scientific papers are written each year about the Oort cloud, its properties, its origins, its evolution, yet there's not yet a shred of direct evidence for its existence. He wrote that with his co-author wife back in 1986. It's been 3 decades, and I can tell you as a professional scientist, professional astronomer, the situation has not changed appreciably since then. This is still true today, though some people have tried to claim a few small objects in the very inner portion of the Oort cloud. The problem is, how can you see these things? They're so far out. I always thought that science was supposed to be the study of the natural world using the 5 senses. That is, if you can't see it, smell it, taste it, touch it, or hear it, it isn't science. No one has ever seen, touched, tasted, heard, or smelled the Oort cloud. So I have to question whether it is a scientific concept. So I would disagree with Carl here when he called it a scientific papers on this. As far as the Kuiper belt, that gets tricky. They have found a bunch of objects out beyond the orbit of Neptune. Some people call this the trans-Neptunian objects, or TNOs for short. Some people say KBOs for Kuiper belt objects. I prefer TNOs because they are very descriptive. That is operational science at its best. KBO, that is historical science, perhaps at its worst on this front. And what's interesting is they claim, and by the way, Pluto is just one of the largest ones of these, and I have to ask the question, well, if Pluto is a comet nucleus, why have we never seen comets that big coming in? I mean, that would be the mother of all comets. It's a lot bigger than anything we've ever seen before, and there are other large objects out there. Also, we have density for some of these things. Pluto, we know its density. We know we know its density of its largest satellite, Charon, and so forth. And I think we know a couple others now, and their densities are about 2 grams per cubic centimeter, 2.0 grams per cubic centimeter. We also know what the composition of comets are, and I've done this calculation several times. I take the known composition of comets and I try to put them back together, the pieces that they exist in, and try to infer the maximum density that you could get, and I get about, at best, 1.25 grams per cubic centimeter. Ergo, the large bodies we're seeing, we have densities for in the TNOs, cannot possibly be comet bodies. And so that doesn't really work anymore. Well, I think my time is almost up. Can I really quickly talk about the early faint sun paradox? Okay, we got a picture here of the sun. It's according to several evolutionary theories, the sun gradually brightens as it ages. This is based upon the physics of how we understand how stars work by thermonuclear fusion in their cores. As you convert hydrogen to helium, you lose hydrogen, gain helium. It changes the mean molecular weight, the number of particles involved, which changes the volume, and PV equals nRT, the ideal gas law. And as you change the volume, change the pressure, change the temperature. When you change the temperature, make the temperature go up, it increases the rate of those nuclear reactions powering the sun. They're very sensitive to temperature, which means you increase the output of the sun. As you do that, it forces more radiation through the outer envelope of the sun, and the sun grows in size a little bit and actually gets brighter. with time. That's based on well-understood physics. Well, how much is it brightened? Well, since the sun supposedly formed 4.5 billion years ago, it's brightened by 40%. Now, if you go back to, say, 3.5 billion years ago when life first originated on the planet, it's brightened by 25%. Could you imagine if the sun brightened by 25%, what with the hand-wringing we would have?
Global warming?
You wouldn't want to tell Al Gore about this. He would have a heart attack, wouldn't he? So 25% is pretty bad since life supposedly arose. Well, you can run the numbers, and I have. This would correspond to a 17 Celsius temperature increase on the Earth. It's interesting to know the average temperature of the Earth today is 15 Celsius. So if it was 15 Celsius today and was increased by 17 Celsius, what was it 3.5 billion years ago when the Earth first formed? I know it's after lunch, but what do you got? It's -2, right? All right? Which in real temperature is what, 28 degrees Fahrenheit, all right? So what would happen if the average temperature of the Earth were a couple of degrees below freezing like that? What kind of Earth would we have? It would be a snowball or ice ball Earth, and you'd have a glacial epoch that would be the mother of all epochs, and it would never end. The entire Earth would be iced over, and it would never get out of that because of the high albedo that it has. Nobody believes the Earth was like that 3.5 billion years ago. In fact, they think the temperature of the Earth has been pretty constant with some fluctuations over that period of time. So how in the world did you maintain the same temperature over all this time? Well, over the past 20 years, I'm aware of at least 4 different explanations for this. When you come up with 4 different explanations, it tells me that the others didn't work, obviously. The most common to believe is that the Earth started off with a lot of greenhouse gases, and with time, the Earth's atmosphere changed, it evolved, so you have less greenhouse gases. So it's kind of reverse of what they're saying is going on today. You needed a lot of greenhouse gases early on to keep the planet warm. Then as the Earth evolves, it becomes cooler and cooler, and what you have are two processes going on gradually to exactly compensate for each other with no feedback mechanism between the two. Would you believe any non-feedback mechanism, 2 mechanisms working independently going on for 3.5 billion years so they exactly compensate for each other? Do you find that hard to believe? I find that very hard to believe. And so I think this doesn't work. And again, where's the evidence for all these things? Well, they've done simulations again. Of course, the simulations always save the day on these things. Well, folks, if the world is only thousands of years old, the Earth, the sun's hardly increased its output at all, and it's not a problem at this point. So those are just some of the evidences I see in astronomy that suggest the world is far, far younger than most scientists seem to think. I thank you today for your attention and your attendance.